Well, welcome everyone to our case study webinar series. This is John Sankey. I'm an engineer for True Blue Technologies, a sales engineering firm that supports in situ characterization and remediation technologies from ASTIS, Tursus, Environmental, TRS Group, NRX, and West Bay Instruments. So this is a series of case study presentations that really focus on the main topic of managing complex sites with high resolution site characterization, which you're going to hear about today, and focused remediation. So today we're pleased to have Dr. Todd Hallahan show how a project manager was able to understand the vertical migration of PCE in a granitic fractured rock aquifer, so they then could plan for the next steps of remediation. Oh, and by the end of the presentation, you'll be able to explain what electrical hydrogeology is to your clients. So Todd's background, who's on the video here, is with us. Todd is a professor and the Sun Chair of Hydrogeology at Oklahoma State University, and serves as the Chief Technical Officer for ASIS. And as one of the recent NGWA McElhaney lecturers, Todd gave talks all over the world. So Todd, thank you for presenting this case study today. You now have the lead.
Thanks, John. And I'm gonna kill the webcam so I make sure I've got enough feed on everything, but I'll give you the Queen's wave and we'll go from there. So I'm a professor at Oklahoma State University in Stillwater, Oklahoma. I'm also a Chief Technical Officer for ASIS, and I do a managed conflict of interest because I have students and there's employees, and those aren't allowed to mix in ways that are inappropriate. But if you got questions about that, just let me know. And then another person on the line is Stuart McDonald, who's out of Loveland, Colorado, running the corporate side of ASIS. So if you want to get a hold of us, you know everybody involved. In terms of today, we do these as rapid fire, try to do about 20 minutes of telling you about things and about 10 minutes of Q&A. It depends on how much I go on about particular details, but you're welcome to stay longer if we've got questions and you want to ask things. You're welcome to stick around and we can keep answering questions, but we'll try to get you out in a half hour if you've got something to get to. And we're recording that. If you need to check it later or you wanted to ask something or show somebody else or something, that's all available as a recording. And there's a CEU certificate. If you need your CEU hours, you get a half-hour credit for this. There's also a Starbucks giveaway, and you can increase your chances by asking questions. And that's the little orange button on the toolbar. And we'll notify the winner by the end of the week. So that's how all that works. And that's the mechanics of this. So I'm an electrical hydrogeologist. People will take chemical data and figure out what's happening across the site, or they'll take water level measurements and look at which way groundwater is moving and think about those things. I take lots and lots of electrical data because it's a really quick way to get lots of information about the subsurface. And so I can collect 10,000 data points in a day and be able to look around. And so this is an example of looking at that in a karst gas station, nice flat surface, but the bedrock down below has a lot of topography. And so taking the scans and figuring out where to target things, putting that in 3D, targeting those locations and figuring out that in this case, the gasoline ran down into a doline and is going to depth. Being able to look at that so that you can target what you're doing and working in the subsurface by being able to have some pictures to work with. You're working at the 10,000 plus data point level and allows you to be able to do really effective assessment of these sites. But it's a hydrogeology technique. It's not a magic detector that you're going to detect a particular compound. It allows you to do hydrogeology of the data density you need to do. The process for that has been well worked out. We've been around for 20 years now in terms of development of the technique and how to do things. So in terms of the ways to get a project to where people can really make good site decisions, that's a multi-step process, and it's not just taking a picture and handing somebody a picture saying, I'm showing you Bigfoot. You got to dart Bigfoot, you got to take a sample, blood sample, and demonstrate these things. So same sort of process, but we're looking for Bigfoot in the subsurface. Now, I use a lot of dogs in my talks. No offense to cat people, but I like using the dogs. So normally when we talk about taking pictures electrically, we talk about things that are conductive and resistive, and I've given several talks where I walk through ways that things are conductive in odd ways. So things like clay are nice and conductive as a geology, But if you want to get really conductive, you need like saltwater spills. Those are great for being conductive. And then microbes, and we're watching microbes on a bunch of our sites chew on things, and they grow into really bizarre patterns. And I call it the mold on the bread because it's a funny shape and it does things like molding in your fridge. So if you've got fine grains or microbes and things, you're going to have conductive features you can look at. On the resistive side, you're looking for, if you're looking for really resistive, you're talking a really clean sand or a really clean gravel that you don't have any fines in there. So something like a fish tank sand or a really clean gravel. But undegraded fuels or undegraded solvents, those are really great resistors. So if you put those in the subsurface, you get nice resistive signatures. And we spend a lot of time talking about those two things, but we're going to look at some other issues today. And the technical one I want to issue is thinking about putting on your electrical glasses and looking at 2D images for dipping fractures and thinking about, I'm looking for features that are not a horizontally bedded thing, or it's not something that's running along as a plane, but you're trying to see where that fracture is at as you're taking a 2D picture of the subsurface. And I didn't abuse that dog. I just pulled it off the web, off of Women's Day magazine. So they're the one that abused that poor dog. But you got to think about putting on electrical glasses when you're doing this stuff. And what are you going to see and how are you going to see it? The same as if you're thinking about putting in a well and you've got to get some napple to come in the well. What are you thinking about for capillary effects in the way you design the well? You got to think about the design of images. So we're going to talk about that technical issue. We're going to talk about some springs in Australia, and then we're going to look at PCE in the northeast of the US. So step one, we're going to have a dipping plane here, and we've got a trapezoid to work with. We're working from the surface. We take it and send electricity down. We get this trapezoid, but we're going to interact with some sort of feature that isn't necessarily horizontal, isn't necessarily vertical either. So how are we going to figure out what dip we're at? And this goes back to if you had a geology background and there's some painful structural geology class that you have a nightmare about apparent dip. It's the apparent dip issue for a 2D plane interacting with a different 2D plane. So if we look at that and you're along the dip and perpendicular to strike, you're lined up so that you can see that 45-degree angle. You can see it electrically in the image, and that fracture, most fractures you're usually going to assume are going to be a conductor in the subsurface. The rock is broken up and ends up being more conductive than the rock around it. There's cases where you can flip that around and make it into a resistor if you put in fault gouge or if you've got napple sitting in that fracture. But a lot of times you're looking for a conductive feature, and it's going to have a little bit of a width to it, and then it's going to have the dip. And electrically, you can figure out that dip within about 5 degrees. There's some issues with getting more precise than that, but within about 5 degrees, you can figure out what that dip is. But you're aligned with the fracture to be able to get the image to come out that way. If you're imaging a site and you don't know where the fractures are, and you come off and you hit it at a bit of an angle, and here we're hitting at 45 degrees, well, now it's going to be a shallower dipping fracture because we hit it with the 2D plane on an angle where the angle in the image plane is actually shallower. So this is where you want to think about collecting images perpendicular to each other so that if you've got dipping features, you can see which way they're going and be able to map that out. And if you're working with geology where you've got a pretty strong fabric to it, you can think about lining your images up to try to get the best odds of getting true dips on things or being able to characterize well. Either way, whichever one of those dips it is, you still have the target to go test what's in that fracture. But in terms of understanding where it's going to or where it might be interacting with other site features, figuring it out is an apparent dip issue, and more than one image is needed to really figure it out unless you've got good constraint on knowing the strike and dip of the fracture already. And then the third option is that we come straight along the fracture and go right along the strike of it. And there you end up with that it's not dipping at all, and it's just a bed in your image. And so this is where you need a set of images to figure out the geology that we deal with, because this might be due to natural fractures, but it could also be due to a DNAPL sinking in a funny way, or other features that aren't horizontal features and aren't vertical features, but that they're going at some angle. So we'll take a look at, we'll go to a nice vacation spot. People are thinking about going on vacation. If you went to the outback of Australia, you could stand on this hill of granite. And this is the little building down there was a telegraph station that was installed to create communication across Australia back in the day. And the reason it was put here is this spot had fresher water than other places in the area. And so it became a drinking water supply, and they built the telegraph station right on this Kingston Fault that's running up and down. And you're standing up on these granitic hills of the Peak and Denison Range granites, and you're looking over the Great Artesian Basin of Australia, which is these sandstones that come up, and the Kingston Fault is separating those sandstones in the distance from these granites in the foreground. And if we look at that in the map view, you can look at that Kingston Fault running along. You got the granites on the left, the sandstones on the right. And we got a couple of images here that are a ½ kilometer long each. And we're looking down about 300 feet or about 100 meters down into the subsurface to see what's going on with where water's coming to that spring and why is it fresher than the other springs in the area. And so when we look at it, and we're going perpendicular to the fault here, and so we've got granite on the left, sandstone on the right, and we can see that most of the water of these springs in this area are coming out of these sandstones. And so you get this very conductive, saltier water coming out at the spring from the two different beds that are dominant for flow parts of the system. And that's the Katanawi Formation and the Algebuckna Formation. But over in the granite, up the fault here, we've got this flow feature coming up, and you're bringing in, the granite actually has quite a bit fresher water, and that's coming up and it's interacting with that spring. And so what you're doing is actually taking an electrical picture of a flow net, and you're thinking about hydrogeology, but you're actually taking data that are showing you the flow net instead of interpreting a flow net or getting enough wells installed to do that. You're just taking a picture of it. If we go perpendicular to the fault, now we can see that water coming up from the granitic side is filling up the fault plane and coming out at the spring, and that the Great Artesian Basin water is coming here dominantly from the south, but the springs running to the north, you know, that mixed water, it's not a lot of this GAB water. It's a lot of it's this Peak and Denison granitic water coming up, and we can start thinking about, you know, historically that this isn't really just a Great Artesian Basin spring, which is what it was defined previously, that in a large respect, the reason it was founded there is because there's a spring in the granite due to the Kingston Fault. But the images look really different just depending on orientation, but thinking about what's going on and what you're dealing with as a flow system, you can put together what's happening electrically and hydrogeologically. So now we'll go up to the northeast US. So it got a lot colder, and we're looking at a very shallow competent granite. Granite sticking out at the surface. There's almost no soil development. And there was an odd distribution of PCE, and the pre-existing plume map was, hey, it kind of out like this, but there's data we don't quite understand. And what they wanted to do was do a thermal remediation. And so thermal remediation is basically prices dependent on volume. And you say, I want to clean up this many cubic feet. You go, okay, I could afford to do that. And you go, how about this many? You go, I can't afford to do that. We got to think about how to do this. And so with this, not a great understanding and some real questions about the conceptual site model, okay, well, we need better characterization if we're going to reduce treatment volume, and we want to see if we can define that more precisely. And you can basically come up with, if the volume got reduced this much, what remediation option is available to me? And it's not necessarily that if you characterize it better, you'd find out it's smaller. In a DNAPL site, you might find out it's bigger or gone deeper. So you've got to want to know the answer, but you have a chance then if you're looking at it and you're saying, I'm defined with wells, but if I got more precisely defined, I can open up some remediation options, and that's what they wanted to do here. So if we look at a line that goes through the source and kind of down gradient for the site, we find we get this resistor here, and that one was tested, and you take a grab sample and you go, yeah, okay, there's a good amount of PCE there. And then you put in the well, and that's got, yeah, okay, so this is a location where we're up by the source. We expected to see some PCE, but the targeting says, you know, that's resistive, but the whole body, all that brown stuff is above the level that, you know, if I'm looking at a porous media site above 250 ohmmeters, I'm thinking about perhaps there's going to be some impacts, you know, because in a porous media site, it's not that resistive, but this is a highly resistive body. And even in that context, if you add liquid resistor in terms of PCE as a separate phase liquid resistor, it makes it even more resistive than the granite. And so it was an interesting lesson of, we were trying to decide as you're looking in granites and things and you're pouring stuff, are you going to get more resistive than that really resistive rock? And the answer was, well, yeah, actually you do. When we look at down gradient and perpendicular to the flow, we get this target that shows up and we go, well, what is that thing and why is it just a depth? And if you look in the upper part of the image, there's all this conductance, and we kind of expected stuff to flow through up there and, you know, to be at the top of the weathered bedrock, not well down into the bedrock, and we've dropped down about 20 feet. And you go, well, how do you drop down in granite? And, you know, we didn't see like a big fault feature and things. What we found is that when you drilled into this thing, you went through hard granite, really low perm, just competent granite, and you hit a sand gravel seam. And then you went back into hard competent granite. So, but in that zone, we're 8 parts per million PCE, so we had plenty of contaminants and we could demonstrate that's the flow path. But, you know, you had to start thinking about, you're imaging this and you've sampled it, but well, what are we actually looking at? And so I didn't know what to call a gravel seam inside of a granite. Usually I have gravel seams deposited by streams, so I didn't know what to do. So I asked a few structural geologists, how do you do a gravel seam inside of a granite? And some of them said, I don't know, which is an interesting answer, because you talk to people that are doing this stuff all the time. They go, yeah, actually, I've done a lot of granites, and I don't know how you put a sand seam in the middle. But I had one that said, you know, not everybody believes in this, but I would call it a deformation band. And I said, well, what's that? Because I didn't know what a deformation band was. He says, well, that's the brittle ductile transformation. And so you're bending the rock and it's ductile, but that you bend it enough that it gets upset and crosses the transition and it goes into a brittle stage where it busts up. And you end up busting up the rock in the middle of a deformation portion that was happening ductilely, but that part of the stress field was such that it was brittle in that part of the stress field. And he says, I can tell you that not all structural geologists believe that occurs, but in terms of data, it's a mechanism for me to get a sand seam in the middle of a granite, and it seems fairly plausible. It still ends up being the transport method for this PCE. So whatever the geologic origins really are, it's still where the PCE went. So when we look at it, the source ends up being more of a line that is actually dipping in space, and it's basically following this gravel that's in the middle of this granite that's of limited extent. It's this deformation band that happens to be near the source, so it ends up getting into that thing and then dropping down another 20 feet and going off this direction. So we end up being able to define where that impact is at. That's the high concentration, and that'd be, okay, you need to heat up a zone something like this to really get rid of the source term. But the down gradient stuff, the mapping out the where the bedrock was competent versus the bedrock being pretty weathered and fractured and things, we mapped that out and got this sort of dip in the middle of the site that in our entire data set through the bottom of it, there was nothing we defined as competent impermeable granite. And so we were basically mapping granite over granite with some funny porous media features inside of it. And those are the kinds of things that you have to deal with of real geology when you're dealing with these hard rock sites and the things you might have controlling the contaminants. But it told us, hey, okay, this is the thing for the source term, and it's this funny feature, and we can fight over what it's called, but it's still a linear dipping feature that would need to be heated to remediate the source. And then we've got controls over the site that is built around the way that the granite's been weathered. And that's a couple of fractures, but a general weathering trend in the bedrock. So that's now much more precise. And now you're thinking about remediation and deciding, okay, so is heating still the best option? How's that volume compared to what we were thinking? If it's a little tube, maybe we inject into that little tube, since it's a gravel tube in the middle of the granite, maybe an injection option becomes best, but your options start opening up because you have a much better idea of why things are distributed in this bedrock. So lessons, and I get this lesson taught to me on a lot of sites I work on. It's really difficult a priori ahead of time. You can't predict what you're going to find in sites. And so, you know, even on porous media sites, I find train cars and boats and different things that are in the subsurface I didn't expect. But you know, figuring out what angle that's at and what feature it is, you still have to biopsy and figure out what it is, but you'll find structures and objects that you didn't predict, and being able to see those and define them really helps with conceptual site models, because a lot of times they'll control your site. It was a great lesson to figure out that PCE in gravel, so you got better porosity, but with a liquid resistor, it's still more resistive than unfractured granite. And if you look at PCE as a chemical, it's like 10 to the 13th ohm meters. It's incredibly resistive stuff. But you know, people think about granite as a resistive, electrically resistive rock, and not compared to PCE. Mapping out the weathering on the granite was really useful when we were delineating flow paths and seeing where the fractures are at, but also where the granite had more porosity just due to general weathering. And then if you get the remediation volume reduced during characterization, you get a lot more options, and so you can think about how to lower your cost for the remediation. And that's where this technology is paying for itself in terms of getting that remediation cost knocked down, or getting to an option that would be a lower cost option. So into the future, we're doing more characterization of these kinds of sites, and it ends up being similar to if you've dealt with seismic. It'd be seismic attribute analysis, where you're looking at the gradients and you're looking at defining what trend things are taking, either on a linear trend or as a plane running through your data set, and doing that kind of work to connect things in space to figure out your targeting. And that sometimes is done through temporal work, and we're doing a lot more temporal work, which is the GeoTrax monitoring. On a short term, that's I want to watch before and after an injection, or before and after a thermal remediation. But on a long term, it's like sticking in a well, except for you're looking electrically. And we're working with the EPA down in the Ada, Oklahoma lab, putting in cables and watching a groundwater system, and you know, getting the protocols for making sure on a regulatory basis people are comfortable with looking at temporal data and how the resistivity is changing as either the groundwater system is changing or as we're doing remediation. So that's the quick and dirty of trying to peek through a granite. But I'd be happy to go through any of them in more detail or answer other questions that you've got.
And Todd, this is Stuart. I'll tee up the questions for you here. We've got a few that have come in already. Rob Thompson and Herb Levine both ask about any depth limitations with the method.
So it's the depth is 1/5 of the line length. And so for 100 feet at the top, we're 20 feet down. If we're 1,000 feet, we're 200 feet down. And we've been working down to 1,000 feet, but you're working with a mile of cable at the surface. So a lot of our projects are looking sort of 20 to 200 feet, but we have several clients that are wanting to look, hey, I don't want to drill 300 or 700 foot holes. Let's take some pictures and let's figure out what we're working with first. And so we do have a set of clients that are going after the deep stuff. So we're getting more experience with that. We just drilled a 700-foot objective on a contaminated site and targeted a place where a lot of stuff piled up in the subsurface. So depth isn't real limitation on most of our sites. It's the urban setting and where we get property access to go laterally to put the longer lines in. That's usually the limit on where depth is. And so if you can work with roads and things, you can do deeper sites. But there's not a particular depth limit on the physics.
Thanks. Rob also asks, what are limitations with surface structures, buildings, et cetera, that might cause signal interference like they would with surface resistivity? Any issues with subsurface utilities disrupting signals?
Yeah, so we go right over utilities and things, and most of the newer utilities, they're actually built for electrical imaging because they coat the pipes or they put them in gravel, and they really do a nice job of electrically isolating them from the surface. So most of the newer ones don't show up, but older uncoated pipes, if you're going right along a utility corridor that's got a big metal pipe that isn't really rusted and it's not coated, that will interfere with an image. So we normally go perpendicular to those, because even if you got one of those in your utility corridor, a lot of times the utility corridor is a place where the contaminants are transmitting. So we go perpendicular to those, and you'll get a little feature in your image if you detect it. but if this method was supposed to be a utility detector, it's not great for it. The other one that is an issue is if you put in a grounding grid. So if you're on a transformer, we get people that have leaky transformers, but they've basically put in a metal mesh all underneath the area where they've put the transformers. And essentially, if we try to put electricity from the surface into the ground, it goes into that grid because that's the way it's designed. And so we can't shoot below those easily. Those are kind of the only two that actually are a problem. And I don't think in the last couple of years we've actually had an image that had much of a utility issue, because we plan all that in advance to, you know, see what kind of issues you might have and plan your shots. It's similar to thinking about, I'm going to stick a well in, and do I have overhead power lines that are going to interfere with putting a mast up, or what am I going to do in the building for drilling a hole? For going into buildings for us, all we need to do is go through a door or window with the cable, or drill a hole in the side of the building and put in a 2-inch hole and put the cable through. But you're just thinking about that and planning that as part of the project.
Yeah, we did a look back recently because we had a client that was very concerned about this issue. And Todd and I did look back for our 200+ projects, and this really hasn't been an issue because we engineer around it. So it's just not much of a problem with our technology. Next question from Natalie Johnson. Are the limitations relative to surface access? Can you look under occupied buildings?
So under occupied buildings, it's an aesthetic question. If we're running through doors and buildings or running through the wall, are we allowed to put a hole in the wall, or do we have to use the doors and windows? Where do those align? And then for the floor, are we allowed to drill a hole through the floor? So on a concrete slab, most folks aren't too upset by that. We put in a 1/2-inch hole electrically coupled below the concrete. We can couple to the top of the concrete, but a lot of times soil doesn't electrically bind with the concrete that well. And if the soil settles out, you give yourself an air gap underneath the concrete. And so we don't know whether that's happening or not. So we find drilling is the lowest effort in terms of making sure the data is good quality, because we've had times where underneath the concrete, you have to put in like an 8-inch stake to go find some soil. If you say, hey, you can't drill through my floor, you can actually couple to it the same as the medical doctors would. So the medical doctors will attach little electrodes to your chest and measure you electrically. You can do the same thing with the plant floor, and we actually use, if we have to be delicate about the floor because it's somebody's, you know, the pristine floor and the previous owner is the one that had the contaminant issue, you can use medical gel. Not all medical gels are conductive, but there's a particular medical gel built to be conductive. So it's water soluble, meets all the health specs. They already built it for us. So we can put a plate on the ground, hook up with that, and look under any building like that. But most of our projects, we drill a hole through the floor for our different stakes, hook it all up, and take the image that way.
And we can also scan around the perimeter of a building to see what contaminants may be leaving from underneath the building in a certain direction. And with the continuous scans, you can figure that out quite readily without going through the floor, if that's a problem. Next question is, at what resolution can you visualize fracture size and spacing?
So a little bit of that is a question back of, well, what size fractures are we talking? So like when we look at sort of larger scale things, and we're doing more geology, which the geology might have a contaminant intent, but that you're looking at sort of larger scale things. If you look at like a 2 to 5 to sometimes even 10-meter resolution, what you're going to find is you'll find a set of fractures running across the image, but you're scaling with the fractures a bit. So you'll find like those 100-meter fractures running along in the geology, you'll see them in the imagery. So if we're talking about like roughly vertical fractures or dipping fractures, as you're running along, you'll see every 100 meter, every couple 100 meters, you'll see that bigger data set of fractures. If you're zooming in and you're looking just under a small site, you might see like one fracture that's really showing up nice in the imagery. But the little tiny fractures just show up as more conductive versus showing up as an individual plane.
Thanks, Todd. Other folks are asking for reminders about length versus depth. So it's 5 to 1, 5 on the ground surface, 1 deep. On our website, on the FAQ section, under technical questions, there's actually a nice FAQ, line length versus depth, that talks about this. So you can go take a look at that. It shows it graphically. Kevin Evans asks, is there any potential for finding anisotropy in the granite body itself so that it makes the fabric is more susceptible to weathering?
Yeah, so that's we've taken, I originally imaged some granite that was unweathered to try to show what a really resistive image looked like, and also to test some data collection things on really resistive objects. And it was actually, we kept finding too many features. Finding something unweathered, you actually start seeing the structure of the fabric of the rock, and like we saw a granitic dike in the granite. And we saw like some bending and folding and stuff. And then we went back to the outcrop and we're looking at it, and you could find, if you knew where to look, you could find like, hey, the granite did change in a line right in this spot, and there was a granitic dike inside the granite. We didn't know that a priori. We weren't setting up the image to image that. So you can see fabrics, but it's difficult for me to tell you a priori that I can tell you what fabric you're going to see and how you're going to delineate it, because it's going to depend on what scale the fabric is controlling the electrical properties of the rock.
Thanks, Todd. We're technically at time, but we have a few more questions, so we're going to continue to answer them here. Let's see here. Edward Clement asks, can this method evaluate multiple aquifers? For example, if the aquifer of concern is below another clean aquifer, will this technology differentiate them?
Yeah, but you're differentiating the stratigraphy electrically, and so it's what's the electrical stratigraphy of the rock, and so it's a discussion where you say, here's my stratigraphy, here's what I've got, and I can try to feed you what that's going to look like in the imagery. But we just did that for 2 aquifers that were separated by a confining unit, and they've been there was some questions about whether they're connected, and the data set said, oh yeah, that confining unit's well fractured in various locations, and those 2 aquifers communicate. And here's the locations where they are communicating, and to the detriment of the lower aquifer. In this case, it was a contaminated upper aquifer. But if you had the lower aquifer just be getting the depth objective set and trying to figure out the remedial objectives for that lower aquifer, are you trying to figure out extent of impacts? Are you trying to figure out particular flow paths? And so it's a discussion about what's the geology, and you're going through the same discussion you do for hydrogeology with wells of how am I going to delineate this problem, but you're doing it with a well that's maybe 1,000 foot wide instead of 2 inches wide. And so you have some differences in the logic about how you set up how you want to look at the problem. But you're just defining how deep do you need to look, and what are we going to be looking for, and what's the best way to get the image for what you're wanting to get to as an endpoint.
And we could talk in more detail about specific sites offline. Just send us an email. We're happy to set up a call to dig more into the details of a particular application. Are there any conditions that lead to blind spots using resistivity surveying? From Brian Sanford.
So the simplest pictures are all resistive or all conductive. It gets more complicated when you make them highly resistive and highly conductive. And so probably the most complicated you run into is a DNAPL with nice fresh PCE with maybe they injected and they got bacteria growing and trying to breathe that stuff or respire it and do those things. And so you get this big conductive biocolony next to resistive source matter. And there you're basically, it's like taking a picture and you're in a room and you want to see dark corners while there's spotlights on at your camera. And you're trying to resolve what the dark parts look like while you have really bright lights on. So it's the bigger combinations that are the hardest thing to take the picture of.
And Todd, somebody has graciously pointed out that we need another L in your email address on screen. So it should be ASTIS LLC if somebody's trying to email Todd. And then I think a couple more questions. Can this be used in existing wells or boreholes in a downhole application like a 350-foot deep recovery well screened 300 feet within nice geology?
Yeah, so you can set up that technique, and we did that early on, but you end up you're stuck playing a game where one foot is stuck somewhere, and you're like trying to walk around and look at things, but you're stuck to that one spot. And so we had tried different combination of downhole and found that we did just as well from the surface. And so it's technically possible, but there's probably easier ways to go about it.
Okay. And another question from Greg Sweel. A site is injecting permanganate to treat TCE. Can the injection patterns be visualized? Yes.
So we've been doing that work, and we've done that with like horizontal wells that are full screen, segmented horizontal wells, and we've done that with vertical wells. And what you do is it squirts. And so we've yet to image an injection that was a plug flow going into a permeable zone and moving out in any pattern that mimics, the nice well equations that you would use to come up with those patterns. It tends to squirt upward into the vadose zone, and it tends to squirt along high K pathways. So you take before and afters, and then we basically have people now designing for the squirt factor and trying to figure out what's the best way to go after it and treat it so that you're not using too much volume of treatment that's going to places that don't need to be treated. And so there's a whole process of doing that electrically that we've been working on. And we've done work with like NREX doing the vertebral wells and things, and worked with some of the directional drilling companies and sorted out approaches to doing that. So we've got a couple examples if you want to see what that looks like, but it's largely that it squirts around, and so you're trying to get imaging of how to control the injection and how to get it to go where you want it to go.
Todd, didn't we do a webinar on that topic?
We did. So we probably even have a video of such things.
Yes. So you will get a follow-up email from this webinar with CEU information, but also I think a link to a landing page that has other webinars recorded. So you can check out our webinar on that topic, or again, contact us. We're happy to walk through that with you in more detail. That's the last of the questions, Todd. We're just a little bit over time. Really appreciate everybody hanging out. Appreciate everybody's time. Again, you'll get a follow-up email from ASTIS with additional information and CEU information. If you have any questions for us, our contact information is on screen. It will also be on that email. So I'll go ahead and close the webinar and hope to see you on our next one. Thank you very much.
Thanks, Stuart. Thanks, Todd.
Thanks, John. Thanks, Todd. Thanks, everybody.